So in this problem we have a log of radius big R and uniform density which is half submerged in a lake. Now if we push down on this log with a small displacement, then the log will start oscillating up and down, and we're asked to figure out what this frequency is of this oscillation in terms of big R and G. So if we push down on the block with a small displacement, delta x, then the volume of water displaced is going to be given by the volume of the rectangular box formed by delta x, the diameter of the log, and the length of the log. So the volume is going to be given by diameter, which is 2 times big R, multiplied by the height, delta x, multiplied by the length of the log, which we'll call L. So this means that the buoyant force from the displacement of the water is going to be given by the weight of the water displaced, which is just going to be the mass of the water displaced multiplied by G. So the mass of the water displaced is going to be given by the density of the water, which is just going to be rho water, multiplied by the displacement volume, delta V, multiplied by G. So if we plug in for our expression for delta V, we get that the buoyant force is rho water times 2 times big R times delta x L. So that's our buoyant force. Now if we use Newton's second law on the log, we get that the net force on the log, F net, that's just going to be the buoyant force, F buoyant. So we have that is equal to rho water times 2 big R delta x L G. And by Newton's second law, that is going to be equal to the total mass of the log multiplied by its acceleration. So we're going to be considering x in the vertical direction, where we've taken delta x to be positive in the downward direction. So the acceleration is going to be given by delta x double dot, which is the second time derivative of delta x. And the mass of the log is just going to be given by its density multiplied by its volume. So the density of the log is just going to be called rho log. And the volume of the log is just the volume of the cylinder with radius big R and length L. So the volume of the cylinder is going to be given by pi big R squared multiplied by its length L. And now we just have to worry about delta x double dot. Alright. So now we've got our equation for the net force. So now we know that rho water times 2 times big R times delta x times L times G is equal to rho log times pi times big R squared times L times delta x double dot. Cool. Oh, we've got that since we've taken the delta x to be positive in the downward direction, the buoyant force is going to be acting in the upward direction. So we need a negative sign here to indicate that the buoyant force is opposite the displacement delta x. So we have that negative rho water times 2r delta x Lg is equal to rho log times pi big R squared L delta x double dot. So now, if you isolate for delta x double dot, you get that delta x double dot is going to be equal to negative rho water times 2 big R delta x Lg over rho log pi big R squared L, which simplifies to, let's see, R's cancel and the L's cancel. So you get negative rho water over rho log times 2 G over pi big R delta x. Now from the hint, we know that rho log is equal to 1/2 rho water. Since the log is half submerged, which means that the density of the log is half the density of the water. So this means that delta x double dot is equal to delta, or rho water, negative rho water, over, and if we plug in for the density of the log, you get half rho water times 2g over pi r delta x, which simplifies to negative 4g over pi big R delta x. So we have that delta x double dot plus 4g over pi big R delta x is equal to 0, which is just an equation for simple harmonic motion, where the angular frequency squared is going to be given by this term here, 4g over pi big R, which means our angular frequency is just the square root of 4g over pi r, pi big R. Now, our frequency is just the angular frequency So frequency is just going to be our angular frequency divided by 2 pi. So that's going to be equal to the 1 over 2 pi times the square root of 4g over pi big R, which simplifies the square root of g over pi to the 3 times big R. So that's our final answer for the frequency of oscillation for the log when it's displaced a small distance delta